Hi students, we're continuing in our discussion of regression analysis, and now we're going to move away from our typical linear models and introduce some nonlinearities, and this will make our modeling a little more interesting. Now, as you know, we've been discussing the idea of multiple regression, and we've looked at some specification issues. For example, what do you do if you have qualitative data, like male or female, right? So we've introduced this idea of specifying dummy variables, and then we even looked at categorical dummy variables when there's not just two different categories, but like marital status, there might be 4 or 5 different categories. But another specification related to our modeling is the idea of nonlinearities. And what we mean by that is when you think a relationship is not a linear one. At this point, we've been assuming that everything has a linear relationship, but that might not be true. So maybe X and Y, two variables, have a relationship, but they're not a line. So if they're not related in a way that creates a straight line, then we have a nonlinearity. For example, we've got something that might look like this. And we see it's nonlinear, it's not a straight line. Instead, our scatter plot gives us something that's a little more curved. So in this particular example, we're looking at jawbone length. So how long is your jawbone in your face versus age? And I did not know this, but apparently as age increases, our jawbone gets longer. That makes sense, right? I'm sure that as we get older, at some point, all of our bones get longer from being a child to being an adult, but they increase at a diminishing rate. So the rate of change slows down. So they get longer and they get longer and they get longer with age, but each increase gets a little smaller and a little smaller and a little smaller. So if you look at this graph right here with our scatter plot, you see that at first when you're young, jawbone length grows pretty quickly. But when you get to more adult age, your jawbone length continues to grow, but it's growing at a much smaller rate. And that's what we mean that when I say it increases, but at a diminishing rate. It continues to grow, but it grows at a slower and slower rate. Another example I found involved registered nurses. So somebody was looking at this and determined that possibly salary and experience related to registered nurses are actually related, but it could be a nonlinear relationship. So in other words, it doesn't fit to a straight line. So maybe salaries for registered nurses grow with experience, but the rate of growth gets slower? Sure, that could be. And so if we look at our graph, we see that, look, okay, it does seem to slow down a little bit, although we don't have as many data points, but you get the idea. So what we're seeing here is what we call a quadratic relationship. And a quadratic relationship is clearly nonlinear. Now, the quadratic form is what we're going to use in our models to show this type of nonlinear effect. And I hope you're not getting nervous because you're thinking, oh my gosh, lots of math. Nope, not lots of math. In fact, it's going to be very easy for us to create the quadratic form in our equations. So let's take a look at a simple model that uses the quadratic form. And here we go. So we've got our dependent variable, y, whatever that is, and we see that that's a function of our explanatory variable x. But you see here that x is introduced in the model in 2 different ways. It's going to enter linearly, and that's our term on beta 0, right? We see beta 0 x. And then we have beta 1 x squared. So what we're doing is adding in that squared term. And that's all we need to do to change our model from linear to quadratic. And what's beautiful about this is by simply adding the squared term, it captures any increasing or decreasing marginal effects. So that idea of, does jawbone continue to grow? Yes, but it continues to grow at a slower and slower rate. That x squared term is going to allow us to capture that extra element. So for us to create this quadratic form, gang, we need both the regular term, the x, and the squared term. So you see x with the superscript with the 2. So that's our squared term. And that's what's creating the nonlinearity here. So we can have something that's increasing, but at an increasing rate. So it's going up, but it's going up faster and faster and faster. Or we could have something increasing at a decreasing rate. Okay, so it's getting bigger, but each time it increases, it's a little bit smaller and a little bit smaller and a little bit smaller. Or something could be decreasing at an increasing rate. So something's falling and it's going to fall faster and faster and faster. And again, there's one more option here that we can think of, but that's what we mean by creating the nonlinearity. Instead of just assuming that the rate of change is constant, like in a straight line, we're going to allow for that curvature. All right, let's look at this visually, because that's going to really help you. We're going to start with this same relationship. So we think some variable y is a function of x, but you see that x enters both linearly, that's the first term, but then also non-linearly, that's the squared term, right? So we have a linear term and we have a quadratic term. And so we have to think about the effect of each one of these. Well, let's start with beta 0. Beta 0 is simply telling us if x, when it goes up, has a positive or negative effect on y. In other words, is there a positive relationship or is there a negative relationship? So if x goes up and it makes y go down, then we know it's a negative relationship. Beta 0 is negative, and therefore the function has a negative slope. For example, let's look at the first picture on the bottom far left. We all agree this has a negative slope. So if it has a negative slope, we know that beta 0 is negative, right? But we also know the fourth picture is negative and the fifth picture is negative, right? So I have three different pictures, three different graphs showing a negative relationship, and they all look different. So we need beta 1 to help us differentiate between these. Beta 1 is going to tell us if this relationship is changing. So we want to know, does it change at an increasing or a decreasing rate? Of course, one option is that it's just constant, and then beta 1 is 0 altogether. So these two things together are going to help us determine which of these 6 pictures are relevant in terms of illustrating the relationship between x and y. So let's determine the signs of the betas for the curves below. Let's start in the far left corner. All right, so we've already said that beta 0 is negative, right? Because we see as x gets bigger, and my axes aren't labeled here, but we know where the x-axis is, right? So if x gets bigger, y gets smaller. There's an inverse relationship. Obviously, beta 0 is negative. But let's look at the rate of change. The rate of change is getting smaller and smaller and smaller, right? We see that the slope is getting smaller and smaller. Well, that tells us that beta 1 is actually positive. In other words, think about what's happening here. The two kind of get combined together. We know there's a negative relationship, but the strength of that negative relationship gets subtracted from. That's beta 1. Beta 1 being positive means that we have diminishing returns. So that's going to add that beta 1 to the beta 0, and in that sense, it becomes less and less negative, right? That's a little odd to think about that way, but let's practice. All right, let's look at the second graph. Do we agree it's upward sloping? It's upward sloping, so what does that tell us about beta 0? Beta 0's got to be positive, right? But do you see that it's getting steeper and steeper and steeper? So we know that this effect of this positive relationship is getting bigger and bigger and bigger. We have increasing returns. So beta 0 is going to be positive, but beta 1 is also going to be positive, and that's why the combined effect gives us that steeper and steeper slope. All right, moving on to the third graph. First, we see that this is a positive slope, right? So if it's positive slope, what does that tell us about beta 0? It tells us beta 0 is positive, but there's a diminishing effect. That positive effect is getting smaller and smaller and smaller. So what does that tell us about beta 1? Let's see if you get this right. Beta 0 is positive, as we just said, because there's a positive relationship between x and y, but the impact of x on y gets smaller and smaller and smaller. So we're taking a little away from that positive effect, right? So think of beta 1. That negative sign for beta 1 is basically like saying it's going to take a little bit away from that positive effect associated with beta 0 being positive. All right. Fourth graph, we see that it's got a negative slope, right? That tells us beta 0 is negative, but what's happening? It's getting steeper and steeper and steeper. In other words, the negative relationship's getting stronger and stronger and stronger. So what does that tell us? It tells us that beta 0 is negative, right? That just tells us the slope. It's negative slope. But combine it with beta 1, where we're saying it's going to become more and more negatively related. That's why beta 1 is negative. All right, what about the next one? So with the next one, we see that we have a negative slope. But what about beta 1? We see that the relationship doesn't change across x. The slope is constant. So what is this going to tell us about beta 1, guys? So beta 0 is negative, but beta 1 is actually 0. In other words, what we're saying is that that term isn't statistically significant. It would be like putting an x through that term. It doesn't turn out to be relevant. What we're saying is that quadratic is not the right specification to fit this relationship. It turns out that it's really just a linear relationship, meaning I only need the first term. And finally, we have an upward sloping straight line. So what does that tell us? Beta 0 is positive. What does it tell us about beta 1? Is there a quadratic relationship? No. So if there's not a quadratic relationship, we would say that beta 0 is positive, but beta 1 is equal to 0. Again, we're saying that the quadratic relationship doesn't fit the data, so we really just need that linear term. We don't need that second part of our model. So there you go. It's a little confusing, guys, but basically we're simply looking at beta 0 to tell us if the relationship is positive or negative in slope, and beta 1 to tell us if we have increasing returns or decreasing returns. Now let's look at some examples of where we might see some quadratic types of models. Let's assume that salary grows with experience at a diminishing rate. Let's assume that that's what we're trying to model. We have salaries for employees, and we think that salaries grow with experience. That makes sense, but they grow at a slower and slower rate. So we can use the following model to estimate this. So if this is really my assumption, then I need a model like this. So our dependent variable is salary, and we see that it's a function of experience. So beta 0 experience, that's our regular term, right, our linear term. And then we've got beta 1 experience squared, which is our quadratic term. And then we have some other control variables. We think salary is related to what field you're in, and we think it's related to the highest degree you have. But you get the idea here. You've got to have both the regular, that linear term, and the squared term here. So what is your prediction for beta 0? What kind of sign do you think beta 0 would have? Well, most likely we're predicting that it would have a positive sign. Gosh, hopefully as you gain more and more experience in your field, your salary goes up, right? So we would be doing our analysis using a hypothesis test that predicted beta 0 to be positive. So a one-tailed test, if you recall. What about your prediction for beta 1? Well, beta 1 is on our quadratic term. So this is capturing how you think experience is going to impact salary across experience levels. In other words, we've already said we think experience makes salary go up, but we want to know, as you gain more and more experience, does the rate of growth in your salary go up, or does the rate of growth in your salary go down? Well, chances are it's negative, that your salary continues to grow, but it's going to grow a little slower and a little slower and a little slower. Here's another example. I found a study that was asking if LinkedIn exposure of their employees matters. Does it affect a firm's revenue? Well, that's an interesting question. So, does having your employees having LinkedIn profiles, does that help? Does that give your firm exposure? And does it translate into higher revenue? Well, that's a good question. So for this study, they collected a sample of 296 companies from the S&P 500. And then they captured the number of active profiles on LinkedIn for their employees. So that's kind of interesting, right? So somebody had to sit and count how many LinkedIn accounts are there for people who work at company 1, at company 2, at company 3. But the idea was they wanted to see if this related to revenues at all. So in other words, is it a significant variable in explaining revenues? Now, what we see here is a scatter plot. It's in log form, so that's a little bit different, but I still just want to show this to you. And on the horizontal axis, we've got the log of employee LinkedIn profiles, how many there are, and on the vertical axis, we have the log of the firm's revenue. Now, don't let log form freak you out. All that means is we're changing our interpretation. Instead of a 1 unit change, it changes it to a 1% change. So it just changes our units to 1 unit to percents. So don't stress about that. What I want you to do, though, is look at the relationship here. And do we agree it's not quite linear, right? We see a slight quadratic relationship between the log of number of employee LinkedIn accounts and the log of revenues. So if I'm modeling this, I probably need to use some kind of quadratic form like we've just talked about. So for example, we might want to use something like this. Firm revenues is our dependent variable, and we see that we've got number of LinkedIn profiles entering linearly, but then we have beta 1 profiles squared. So we're capturing the quadratic term. Now, again, they're doing a log model. I don't want to go into that, so I'm keeping this really simple. But what's the suggestion for beta 0 here? Based on the graph, what's our suggestion for beta 0? Well, it seems like beta 0 is going to have what sign? Positive, right? It looks like it's an upward sloping function. Well, that makes sense. The more profiles there are, then there's more exposure for your company, which means revenues are going to go up. Well, that's interesting. So maybe as a business owner or a manager, you want to have your employees all create LinkedIn profiles, good professional LinkedIn profiles, maybe. What's the suggestion for beta 1? Well, the suggestion for beta 1, so remember, what is beta 1 capturing? The rate of change. So we've already said more profiles is good. It makes revenue go up. What we want to know is, as more and more profiles are added, is the impact on revenues an increasing one or is it a decreasing one? Well, if we look at the graph, it appears to be that it's an increasing function, right? So we would call this increasing at an increasing rate. It's not a very quickly increasing rate, right? It's not super, super duper quadratic looking. It's kind of mildly, but it still looks like it's positive. So what does that mean? It means that revenues grow at an increasing rate in relation to number of profiles. Or if that's not clear to you, let's say it another way. As profiles increase, revenue grows at an increasing rate. So more profiles is better, and the increase in your revenue gets bigger and bigger and bigger with additional profiles. So maybe there's something to take away from that. The next study we're going to look at is a study on weight. And we see that somebody is modeling weight using both age and we see age squared. So this is clearly a quadratic model. I don't have to read the study to know. I can just look at the specification and I know that they're fitting a quadratic. The effective age changes as we get older. All right? That's basically what we're saying. The effective age on weight is going to change as we get older. In other words, it's not constant. If I think the effective age on weight is constant each year, we gain the same number of pounds, I don't need the squared term. But here we're just assuming that the effect of age, getting a year older, it's not constant. It's going to have a nonlinear effect. So the effect of another year is not the same when we're younger versus when we're older. So the effect of getting 1 year older will not involve the same weight gain when we're young versus when we're old. So let's see what we can determine about the conclusions. Let's start by interpreting the linear variable that's simply age. So how do we interpret this? First, let's look at significance. And we see that's a p-value. They called it sig for significance, but it's really just a p-value. Or you can use the t-statistic, which is 5.07, which by now you're probably getting the hang of. That's pretty big. So we know that age is significant in impacting weight at the 99.9% level. So age is definitely something that impacts weight. And we also see that it's positive. Now, anybody who's in my age bracket already knows this, that as we get older, our weight goes up. It continues to go up. At least it has for me. I don't think I'm an anomaly. So you're not telling me anything I probably couldn't predict, but you are allowing me to quantify it, right? So let's look at the coefficient. We see the coefficient of 1.87. So what does that tell us? For an additional year, weight increases by 1.87 pounds. So for each additional year, weight increases by 1.87 pounds. And that's holding all other variables constant. So notice there's some control variables here. They're controlling for height, for if you're female, your family income, if you're a smoker or a non-smoker. But here's the thing. When we are estimating that linear term in the quadratic, right, just the age, not the age squared, that's giving us the relationship at age 0, which I realize is a little confusing because at age 0 you don't really have a weight. But just go with me on this, right? It's estimating at age 0 because, remember, the effective age is going to change as we add years. It's not going to be 1.87 pounds every single year. That's going to change. And it's going to change when we look at the age squared term. All right, the squared age term is what's going to tell us how it's going to change. How It won't be 187 pounds every single year. It will tell us, is it going to be more than this? Is it going to start to go up? Is it going to be less than this from year to year? That's the role of the squared term. So let's take a look at the squared term. How do we interpret the age squared? Well, again, our p-value, which is what they're calling significance at the very right column, it's 0.000. So a p-value of 0.000 means we have significance at the 99.9% level, right? At the highly, highly, highly confident, right? Same with age. So we're highly, highly confident that this was not a relationship found purely by chance. It's also negative. So let's think about this. Okay, age was positive, age squared is negative. So do we agree? At this point, we can say that weight, when it comes to age, increases at a decreasing rate with respect to age. So let's say that again. Because we know it's a positive relationship with age, we know it's upward sloping, but it's going to increase at a decreasing rate, right? Now, we can interpret this. For every additional year of age, weight increases. That came from the linear term, just age. But it increases at a decreasing rate. And specifically, we know each additional year decreases our gain by 0.02 pounds. So each additional year, it decreases our gain by 0.02 pounds. So we're still increasing in weight, but that increase gets a little smaller and a little smaller and a little smaller. So again, be clear, we're still gaining weight over age, right? Over time, we're still gaining weight, but we're gaining a little less and a little less and a little less each year, holding all else constant. So if I asked you to graph this without having to worry about being super precise, could you draw it? Does everyone agree it would be upward sloping, but it would kind of be half of an upside down bowl, right? It's going to go up, it's upward sloping, but it gets less and less and less steep. Now, what if the squared term in your model turns out to be not significant? If it's not significant, right, like experience squared or tenure squared or age squared isn't significant, well, that suggests that maybe the quadratic isn't the right fit after all. And if the quadratic is not significant, then we're back to that linear form. So maybe the relationship really is linear after all. So it's that squared term in our model that helps you learn if the quadratic is the accurate type of format, if that's the real nature of the relationship. Now, we also want to make sure we understand and are careful about the effect of outliers. Having just a few observations in the tails could be problematic. So look at this observation that I've circled in red. It's kind of an outlier. And we see that it's making the relationship look more quadratic because it's pulling that blue curve, right, to the right, it's pulling it down a bit. And we see that's a bit different than the linear model. So that outlier there might be making the relationship look quadratic when it's not really, when maybe it's not. So if we were studying this, we might want to compare the linear model to the quadratic model. And there are ways where we can actually see which is better. For example, we might use an F-test to compare to see if that quadratic term is useful. We're not going to necessarily do that at this point, but it is a possibility. So let's recap. We've talked about a specification issue Specifically, what do we do if there's a nonlinear relationship? And we answered the question by saying, look, we're going to model with the quadratic function. And the quadratic function isn't anything super scary. It just requires us to have a variable enter both linearly and in squared form, like x and x squared. It's important that you remember what each does. X, the linear part, captures if the relationship is positive or negative. Is this upward sloping or is this downward sloping? But the squared term, x squared, is going to capture if the relationship is one that's changing at an increasing or a decreasing rate. So at this point, you should be able to understand the role of both of these components in the quadratic. You need to be able to look at econometric results and see if they're significant, and then you need to be able to interpret them, and we've practiced this. And of course, if you know what's significant and you know the sign, then you can also tell me what the shape of the relationship is if we were trying to graph it. So thanks for listening, guys. Let me know if you have any questions at all. And other than that, have a fantastic day.